Hi guys. Today we are going to start chapter 5. Chapter 5 is about binomial distribution. So from this chapter we are changing our gear and we are entering a new field in statistics. Let me describe how this chapter differs from the earlier ones. So uh, we are going to consider a model. So in general, in any science, a scientific model of a model is a simplification of phenomena using assumptions, right? So model, like almost every science uses some kind of models. Like even in economics, there are like supply demand model or like monopoly market model, and there are many different types of models. And what you learn in microeconomics and macroeconomics are also kind of models like Keynesian model, ISLM model, like Heckscher-Ohlin model. If you have not heard about that, there are bunch of models. And in statistics, of course, there are some models. As I said, what we are going to do here is in a statistical model, we are going to make some assumptions so that the full distribution, the entire distribution, can be perfectly summarized by a small number of parameters, right? That's what you're going to do. Small number of parameters contains every information of the entire distribution. If that's possible, it would be really nice. And of course, we need some assumptions, and it simplifies the analysis a lot. So then, what's the probability and average we learned earlier? They are not models because they first they do not contain the full information of the distribution, and second, they do not require any assumption. They are just something to be calculated, but they don't require any assumptions. The only thing you need is that the random variable is quantitative. As long as the random variable is numerical, there exists average. So an average is not a perfect information of the distribution. So probability and average can be described more like it's more about description rather than a perfect summary. So in chapters 5 and 6, we are going to learn two important probability models. Chapter 5 is about the binomial distribution, and chapter 6 is about the normal distribution. So um, let's start how we are going to build a model and what's their properties. So we have these chapters from the textbook. If you would like to, if you would like some more reading, then you can simply search for binomial distribution. Search binomial distribution on Google, like binomial distribution lecture notes or like slides or exercise. Then you can see a lot of materials online. So it shouldn't be uh, difficult to find additional resources. Okay, let me start with a warm-up question. Uh, think about these five random variables, and they are number A. A is the outcome from a coin toss. B is the gender of a randomly chosen person. And C, whether a randomly chosen student has a passing grade in calculus or not. And D, the price of a randomly chosen dish on a restaurant menu. If the answer to a true-false question of a randomly chosen student, then what do you think is different from the others? It, mm, just a warm-up question. And the answer I had in mind is this. because price can take any number, but the other guys are more it's more like binary, yes or no. So outcome from a coin toss is heads or tails. Gender is male or female. Uh, Whether a randomly chosen student has a passing grade in calculus is either pass or fail. Answer to a true-false question is either true or false. So in the other random variables, in the four random variables, the possible outcomes are, there are only two possible outcomes. Possible outcomes are yes or no type. But the price can take a number of numerous, infinitely many possible outcomes. That's the major difference I thought when I make this question. So we are going to call this kind of random variable as a binary random variable. So we say that a random variable is binary if there are only two possible outcomes. That's the point. It can be yes or no, male or female, like true or false, whatever, pass or fail. There are a lot of examples as you can see here, win or lose, positive or negative, right? You can think about a lot, but it does not matter. All these kind of examples share the same properties. So we are going to call, in general, we will label them as success and failure. But it does not mean success is good and failure is bad. It's a convention, it's tradition in statistics to say one event is success and the other is failure. So a failure can be something good, like something like a win. Win can be labeled as failure, and lose can be labeled as success. Just convention. And also conventionally, success is encoded as number 1, and failure is encoded as number 0. So we, as you know, we want to make a random variable numerical value. So we will use 0 and 1, which is the typical coding. We are going to code the outcomes into 0 and 1. And also it does not matter. It doesn't mean 1 is larger than 0. So you can put 1 on wins and 0 on lose, but you may change the labeling. Like you can put 1 on lose and 0 on win. Does not matter. So there are two outcomes, and I don't know what's what, and there is no ordering. There is no judgment. Nothing is better than the other. But still, we are going to call them, just for convenience, we are going to call them 1 and 0. 1 is success, 0 is failure, right? It's a convention. And then let's think about the random variable. So think about a random variable x, and from now on, when I say binary random variable, automatically I will assume that it takes 0 and 1, right? So 0 and 1 is if I don't say anything more than that, binary random variable is simply 0 and 1. Then we'd like to study the properties of this random variable. Then what do we need to know? There are only two probabilities. If you know these two probabilities, that's all. Then you know everything about this binary random variable. So this is the simplest possible random variable we can think of. So we just need the probability of x equals to 1 and probability of x equals to 0. And we can simplify even more, because if you know one probability, then the other probability is automatically 100% minus this guy, right? So for example, if you know that if you let if you denote this probability as p, then the other probability should be written as 1 minus p, right? So in the end, what you need to know is just one probability. If you know P, this P, then you know this probability. So you know everything about this random variable. This is the first statistical model you obtained. So under the assumption that there are only two possible outcomes, then any random variable satisfying that assumption will have the same property. So P is sufficient to describe the entire probability distribution. So we call P as the parameter. P is the parameter of a binary random variable. And probability distribution table can be written in this way. There are two possible outcomes, and their corresponding probabilities are P and 1 minus P. So one parameter describes everything. That's the reason why we study statistical models. Okay, I think I'm going to stop here, and I will continue. I will continue to the next video, and we'll study more properties of a binary random variable. See you in the next one.